Welcome to another video from SkyRadar. Today we are going to talk about the two-dimensional constant false alarm rate CFAR. In order to investigate CFAR, we are performing a live measurement with our 8 GHz radar and working with the FreeScopes. This simple example will consist in observing the impact of CFAR 2D on the Doppler range heat map. Let's start building the signal chain in the FreeScopes. We will start first with the signal receiver, as always. Then the second block will be to raw data, which will connect the live measured data to the FreeScope. Next comes suppressors. We have talked about suppressors in previous videos, and we are going to use this block to suppress the source of the antenna. So, as we are working here with CFAR 2D, we need to generate two-dimensional signals. The output of suppressed source will be one-dimensional signal, therefore we are going to use the burst function to generate from the 1D signal the two-dimensional signal. The next block on the chain will be the two-dimensional fast Fourier transform, which will give us the information of the Doppler range. So after FFT2D, we are going to connect the CFAR 2D, and we are going to observe here the heat maps. So one heat map will be connected at the output of the CFAR 2D, and the second heat map will be connected to the output of FFT2D. So in order to see the difference in the heat maps with and without the CFAR two-dimensional function. We are connecting an A scope at the output of suppressors just that we have a better idea of how our targets look like and in which range in meters are they away from the radar. Now, as you can see, we are going to connect now one of the heat maps at the output of the FFT2D. So this heat map shows the Doppler range of the signal, the Doppler range view of the signal without the CFAR 2D effect, and the second one has the constant false alarm rate included. Let's reorganize a little bit so that we can see the measured signal better. And here on the A scope, as you can see, we have a very high peak. And as I said, so this is the noise coming from the antenna. So we are going to use this function in order to suppress that noise. And now here we see a static target at roughly 5 meters. But first, let's try to understand what CFAR is. And for that, I'm going to show you a short part of our training manual in which you can find detailed information about all our algorithm and some detailed exercises. So here we see the one-dimensional CFAR consisting on the cell under test, guard cells, and the range cells. We have seen CFAR 1D previously, and the CFAR 2D actually is built on top of the CFAR 1D. The only difference here is that we don't have anymore only one array of data, meaning we are not observing anymore the range, only the range domain, but here in this case we are looking in both dimensions, the range and the Doppler, and you can see the data window extends in both domains. Now let's come back to the FreeScope and observe. After we click on the CFAR 2D block, we can see on the left side the alpha, the range window, the range guard, and Doppler window. As you can see on the screen, I'm doing some movement, going back and forth, and now I'm start changing the parameters and observe what will happen. As you might remember, the alpha is the parameter which is defining the threshold for the probability of false alarm. This means if we have a low alpha, this threshold will be low, and if we increase the alpha, this threshold will be high. So there is a risk when we put the alpha too high that we start missing our targets in the heat map. So here in this case you can see how the CFAR 2D delivers a way better result compared to the heat map without the CFAR 2D. So you can see on the left side the noisy as I'm moving back and forth. The heat map is not showing only me as a target but also a noisy column, and that is pretty much avoided on the right side where we use CFAR. So here I have increased the range window, and now I decrease it so that you can see the difference between high and low range window. So what the range window do is, as we take a larger amount of information in the range domain, it will try to estimate the noise floor of the whole window, and the higher that window is, the better will be the estimations done. And the same principle works also for the Doppler window. So if we have a large Doppler window, then we will get a better estimation about the noise floor in the Doppler axis. So now you can see if I put range window, range guard and Doppler window to the maximum, I get way more cleaner targets, moving targets on the heat map compared to the one without the CFAR 2-dimensional. We can see here the range guard, and if you remember, the guard cells are the cells which are around the cell under test, which we have to ignore because of the side lobes coming from the target. And the range guard is the number of these guard cells in the range domain. So the higher this value is, the better the signal will look in the range domain, so the clearer it will be from the noise. However, as you can see on both graphs, on the left and on the right side, we see some static reflections which still appear in the heat map even though there is no target moving there. And these reflections are there due to corner reflectors which are in the environment of where the radar is taking the measurement. So if we want to avoid that one on the right heat map with the help of CFAR 2D, we can increase the alpha at very high levels, and those targets will be slowly suppressed. However, there is the risk of losing the information from the moving target, which means if the alpha gets high enough, then we will not see anymore the moving target on the heat map. So with the help of CFAR 2-dimensional, we can suppress the noise dynamically in both directions without putting any static values, which will avoid the human error in deleting the existing targets. However, we have to be careful in order to pick the right alpha, the right range window, range guard and Doppler window size. And as we saw, so the best range window, range guard or Doppler window will be, so we will get the best result if we take the maximum of them and if we take a reasonable alpha. However, sometimes we will get a very clean result in the screen even if we take lower values for these windows. and doing so we will reduce the computational power of the algorithm. So there should be a good trade-off between the computational power and the satisfactory result shown in the screen. So in this video we went shortly through the CFAR 2D function, and more information about that you can find at our homepage. Stay tuned, more to come.